To understand how a straight line is oriented in 3 dimensions, we measure the angles it forms with the positive x, y and z axis. We call these direction angles. If we take the cosines of these angles, we get our unique direction cosines denoted as L, M and N. A key property to always remember is that the sum of their squares is always equal to 1. Because dealing with exact direction cosines can lead to messy fractions or square roots, we introduce direction ratios, which are any 3 numbers proportional to the direction cosines. While a line has only one set of unique cosines, it can have infinitely many sets of direction ratios simply by multiplying or dividing by a common scale factor. If you have two distinct points in space P and Q, exactly one straight line can connect them. To find the direction ratios of this line, you just find the differences between their coordinates x2 minus x1, y2 minus y1 and z2 minus z1. To scale these down into true direction cosines, you simply divide each coordinate difference by the total straight line distance between the 2 points. So that is the distance formula. PQ equals under root x2 minus x1 whole square plus y2 minus y1 whole square plus z2 minus z1 whole square. So similarly, the distance ratios and the distance cosines can be calculated. So equation of a line passing through a point and parallel to a given vector. To log down a line in space, you need a starting anchor point and a clear direction trajectory, right? In vector form, any point R on the line is found by starting at our known vector position A and moving a scalar multiple lambda along the parallel direction B. When we break this vector statement down into its component algebraic coordinates, we get the symmetric Cartesian equation. Notice how the fixed coordinates are subtracted on top and the direction ratios sit cleanly in the denominators. Next is equation of a line passing through two given points. What if we are only given 2 points instead of a point and a vector? We use the exact same logic. We use the first point A as our fixed starting anchor and we find the direction vector by subtracting A from B. In Cartesian form, this means our denominators are simply the differences between our two fixed coordinates. So that is the Cartesian equation. Next is the angle between two lines. When two straight lines cross, or even if they pass by each other at an angle, we measure the sharp angle theta between them by looking directly at their direction vectors b1 and b2. By taking their dot product and dividing by their magnitudes, we isolate the cosine of the angle. Two lines are perfectly perpendicular if their dot product evaluates to exactly 0. Conversely, they are parallel if their direction components scale perfectly proportionally to one another. So that is the condition, and this is the Cartesian angle formula using the direction ratios. So perpendicular, it is important condition using which we can solve problems, and this is the condition for parallel lines. The ratios are equal. Next is the shortest distance between two lines. So in 2D plane, lines must eventually cross unless they run parallel. In 3D space, however, we can have lines that cross completely over or under each other without ever touching. They are called skew lines. The shortest the shortest distance between two skew lines is measured along a segment that drops perfectly perpendicular to both paths at the same time. We compute this mathematically by evaluating the cross product of their trajectories, dotting it with the displacement vector between their anchors and normalizing it. If the lines are parallel rather than skew, their direction vectors are identical, and we switch to cross product format to measure the fixed spacing between them. Next, moving on to some problems. So problem 1 is finding direction cosines from ratios. So the question is, if a line has direction ratios 2, -1, -2, find its direction cosines. So the solution given: a equals 2, b equals 1 and c equals -2. First, we calculate the common normalizing denominator, that is under root a square plus b square plus c square. So the calculation comes out to be under root of 9, that is 3. Now, after getting the common normalizing denominator, we determine each individual direction cosine. So L is a upon under root a square plus b square plus c square, that is 2 by 3. Similarly, for m and n, we use b and c instead of a, and the denominator is same. So the direction cosines are 2 by 3, -1 by 3, -2 by 3. Okay. Next problem is proving lines are perpendicular. So the question is, show that the line passing through points 4, 7, 8 and 2, 3, 4 so is perpendicular to the line passing through points 0, 3, 2 and 3, 5, 6. So the 4 points are given. So one line is through 2 points and another line is through another 2 points. So the line L1 passing through A and B, the first 2 points, we calculate the direction ratios. Using points A and B, we calculate for line L1, and using points C and D, we calculate for line L2. It's not there is a mistake on the screen. Actually, the A1, B1 and C1 is not written, but you can calculate it similarly, right? So next, for the condition for perpendicular, is given, so we can test that condition. So it's not coming out to be 0, so we need to apply a correction check based on the coordinates, right? So let's check if the problem vectors match the standard orthogonal examples. So points A and B are modified. Yeah, right? So now using these the different points, and we check for the orthogonality. So calculating the direction ratios. Okay, next step is calculate direction ratios of L1. Okay, orthogonality, and we can calculate the L1 and L2 for passing through C and D. So the condition, if the lines are perpendicular, if and only if A1 A2 and plus B1 B2 plus C1 C2 equals 0. So since the sum equals 0, the lines are strictly perpendicular. Next, moving on to the problem 3, that is the shortest distance between two skew lines, right? So question is, find the shortest distance between lines r equals I cap plus 2j cap plus k cap plus lambda I cap minus j cap plus k cap, and r equals 2I cap minus j cap minus k cap plus mu times 2I cap plus j cap plus 2k cap. So consider like r1 r2 or something, different naming you can take. So yeah, so identifying the position and direction first. So A1 and A2, A1 B1, A2 B2 is there. So the next steps, it will require like around 5 steps to get the final answer. So the first step is compute displacement vector A2 minus A1 as shown on screen. Next step, step 2 is compute cross product B1 cross B2 using the determinant, right? It's easy to calculate using determinant. Next, moving on to finding the magnitude of B1 cross B2. So using the formula, we calculate it as under root 18, that is 3 under root 2. Fourth step is evaluate the dot product calculation. Oh yes, B1 cross B2 dot A2 minus A1. So calculating it, we get minus 3 minus 6, that is minus 9. So applying these values to the shortest distance formula, we get the distance as 3 root 2 by 2 units. So that's all for today in this video. Thanks for watching. Like, share and subscribe. So you can comment if you have any doubts, and see you in the next video.